questions on lab 2. So a 40 by 40 drum with at least 3 different tones produced by pushing 3 different buttons. Of course, if you put row, eta, and nonlinearity onto the switches, you could do 2 to the 9th different sounds. Solver, anything else I need to talk about?
20.8 microseconds, how do we demo that?
How do you prove that your solver finishes in 20.8 microseconds?
Yes.
Okay. In the Verilog, you could, when you enter the state which says you have a slot in the FIFO empty, you set a GPIO pin high. When you go to the next state, you set it low. Done. Hook the oscilloscope to it, show that that pulse length is less than 20 microseconds. Actually, it's going to be from the start of one to the start of the next one. So it's going to be from here to here. That's very convincing because it's a hardware readout. No interpretation, no calculations necessary. You just set it high when you enter that state. You set it low when you exit the state where you do run the solver.
We should just show that it works synthesizing at 48 kilohertz. Like it has to meet the time requirement, right? If it,
Yeah, this proves that it meets the time requirement. Okay, so what would happen to your solver if it actually took longer to calculate than 20.8 microseconds? What would be the audio effect? Have you tried that?
No.
I have.
Oh.
You can imagine if it failed in a certain way that it would just be an octave low. Then it would do every other sample. And so you could duplicate samples and do it run an octave low. But what happens if you don't do anything special is it dies completely. However, I want it more quantitatively than it works perfectly, it dies completely. How much of this did you actually use? Right. Generally, measure means give me an output that shows the amount. Yes.
So not just having it set the pin high as soon as it enters the state and then low right away, but
wait till you exit the state. Wait till the solver is done.
Okay.
So yes, it could look like this. Ideally, the solver would spend most of its time in the solver and very little time outside the solver because that way you can do the most notes. Or you've written inefficient code, one of the two. What else? Let me remind you that I have 5 sets of speakers which have decent bass response. The little speakers that we have in the lab laying around every place, the little ones like this, have terrible response below 200 hertz. The big drums that you're going to build will probably have a fundamental of around 50 to 100 hertz, particularly if your row is relatively low. So you need to use better speakers, or all that you will hear will be the distortion overtones. So if you need a big set, let me know. I've got them in the cabinet there. I don't leave them out because they get merged, tangled with everything else on the tabletop. Oh, while I'm looking at them here, yes, Ryan has graded Lab 1. You can pick them up at the end of the lecture. What else? On Lab 2. Anything else? So we were talking about Mandelbrot set last time and the time before, how to actually do the calculation to compute this fractal monstrosity. And so there's the formal iteration of the complex numbers, and then there's some optimization stuff I talked about, which says how do you cut the number of multiplies down, how do you streamline the pipe, the complex arithmetic pipe. And what we still need to do is to figure out how to do the output. So I wanted to talk a little bit more about the VGA interface and how to hack on it. And maybe talk a little bit about floating point. Because you could use floating point for this particular exercise. So the problem is, with output, is that the QSys bus, let's say, if you have VG, if you're using the, what's it called, video subsystem, you can only write, you can single thread the writes to VGA memory, because the VGA subsystem expects its display memory to be a QSys device. Maybe make that slightly more concrete by going back and looking at the top level QSys here. There's a VGA subsystem which has a pixel DMA master which is going up here and disappearing off screen, but which, if we extend it up here, goes to SD-RAM. So SD-RAM is being used to provide pixel color. So on every VGA clock, there's a VGA clock happening at 25.175 megahertz. On every VGA clock, the VGA subsystem is sending out an address that's causing SD-RAM then to send back a color to the display subsystem. Can only do one at a time. The memory is single threaded, so that if you have a solver, let's say a Mandelbrot solver that's trying to write to that memory, it can't write to the memory while the VGA is displaying from the memory. How often does the VGA run? All the time. It has no external memory, so it runs all the time, except for some sync pulses. So that sounds horrible. It sounds like you're dead in the water, except you're not, because The VGA only requires a sample every 25 at 25 megahertz, but the memory runs at 100. So you actually have 3 cycles in between each VGA read to which you can write to the SD RAM. The question is that fast enough? Is it the fastest way to get results from multiple solver pipes? And remember, you're going to this lab, it's a flat-out performance lab. So you're going to be graded on how fast you can draw this image, how fast you can draw a Mandelbrot set. So more solver pipes means faster response. If you have 20 solvers running, and only one at a time can write to the SD RAM, then 19 of them are going to be waiting, at least part of the time. And so the question is, how do you get around that? One way to get around that is to break the VGA display into 20 pieces and have each solver write to its own piece of memory, its own carefully hoarded piece of memory. And then at 25 megahertz, that same memory is traversed by the VGA controller to grab colors back for a given VGA address. The VGA subsystem, as defined by QSYS, is not designed to do that. It's designed to display from one block of memory. That means that if you're going to go to the highest performance Mandelbrot solver, you have to write your own VGA controller and then link memory to it. And to draw that out again, if this is VGA space, you might have stripes here corresponding to solver 0, solver 1 through solver n. And each one of these is going to be mapped into a separate RAM block. Separate RAM block 0, 1, n. Each one of these is going to have its own dedicated solver, which the solver can therefore write to the RAM with no contention, so it never stalls. Solver 0, solver 1, so on. Then the VGA controller is going to mux the output of these RAMs to decide what color pixel to draw in each section. As long as you're in the top section of the screen, it'll read from RAM 0. When you go into group to the second stripe, it reads from RAM 1. From the nth stripe, it reads from block N. Because the memory is dual ported, the solver can still write at all times to the RAM block, even when the VGA is reading from it. So there's no memory contention, either between solvers or from the solver to the VGA. You can't do better than that. However, then you have to write your own VGA. And I haven't done that for the DE1, but there was a student who did that a while ago for the DE2115. So the page is called VGA examples. That's the search term. And he wrote a control module which is highly parameterized, but has a fairly easy interface. This is the notorious Schuyler Schneider, who wrote all kinds of bizarre stuff. So the interface is, you can actually define a cursor position and a cursor color. Ooh, how handy for a cursor. It takes as input the color of the pixel. I here stands for input. Red, green, blue. Where does it get that color from? The memory pointed to by either address or concatenated coordinate X and coordinate Y, depending on whether you like to think linearly or in XY coordinates. So this module, the VGA controller, is going to produce an address. 1 or 2 cycles later, that's a parameter you get to choose. Back out of memory comes a color, which goes into these 3 inputs. Also, this module then connects to a series of I/O ports. These are physical I/O off the FPGA, corresponding to the red, green, blue, async, vsync, and so on connections that go to the monitor. So these represent connections from the FPGA to the monitor, and all have to be connected, obviously. The contents of this VGA controller are really just a state machine that steps through the timing requirements for VGA. And the timing, oh, that's a horrible image. So, horizontal timing is, you have a time when the horizontal sync is low, and no video, no memory accesses are required. But all the time the async is high, you're required to do memory accesses because that represents one line of the display. And therefore must output 640 pixels during how many microseconds? D. 25 microseconds. So you all of this time you're doing memory accesses. The VGA controller is doing memory accesses, and the state machine is making sure that all of the sync levels are correct for you. So all you need to do to make this run is to make sure the parameters are correct on the parameter file, which they probably are, and provide it with a color for each different pixel. The easiest way to test it is bring up this VGA controller. Don't even hook memory to it. Hard code a red, green, and blue value into its input. Hard code red 0, green 255, blue 0. And you should get a green screen. Or you say, if coordinate X, if coordinate Y is less than 240, make it green, otherwise make it blue, and then you'll have the top half of the screen be green, the bottom half be blue. That's how you test the controller. Once you get the controller running, then you can connect memory to it so that these addresses get feedback, color feedback information from memory. Now I do say in here, you can't use Schuyler's PLL module because that was for a different architecture. So you're going to have to generate a phase lock loop to convert clock 50 to 25.175. By the way, clock 100 is also available in most of my examples because there's a phase lock loop in the QSYS description which generates a 100 megahertz clock. Josh?
Would using just a 25 megahertz clock be sufficient?
No.
No.
It's almost good enough. Just doing a clock divide is almost good enough, but not quite. So you need to generate a PLL that takes clock 50 as an input and generates 25.175 megahertz as an output. Now, to make that more concrete, I suppose, I add a little bit to the IP library overview, how to do a phase lock loop setup. First of all, you invoke the phase lock loop wizard, of course. In the upper right corner of the design area, there's an installed IP directory. Under basic functions, there's phase lock loop. You ask for the phase lock loop, the Altera phase lock loop, and it opens up a little dialog box in which you choose the name of the .v file that you want. I call this video underscore PLL.v. Once you do that, then it opens up a dialog which gives you a lovely little image of the I/O lines from the video PLL. There's a reference clock, 50 megahertz. There's an optional reset, which you have to keep out of reset most of the time. There's an output clock, and there is a binary signal that says locked, unlocked, which you can optionally disable. You're going to put in a reference clock at 50 megahertz. You're going to ask for 25.175. The design tool tells you that it can actually generate 25.175644. It's close enough. And you don't want any phase shift. Once you enter those features, you can go down here and press, wherever it is, finish, and when you do that, then you will get a little dialog box saying, I'm generating this junk for you and putting it someplace. And then the module interface is in the video PLL.v file. And there's an input which is run clock, or input which is reset, and output which is out clock and lock. That's the whole interface. So they're easy to set up. The advantage of using a phase lock loop rather than just writing a clock divider is, first of all, the frequency is exact, and secondly, when you use a phase lock loop, the output clock appears on the clock distribution network instead of a logic line. The clock distribution network has much better timing characteristics and attempts to have all parts of the chip get the clock signal at the same time. So it's much easier to synchronize. So to set up the video controller, you're going to have to instantiate a phase lock loop. You're going to have to instantiate the VGA controller, and then figure out how to interface several memory blocks to it through some sort of muxer. And after you do that, you'll probably get a factor of 2 or 3 increase in performance. Significant, not gigantic, but significant. Maybe a little high.
I have this.
Yeah.
So what if we use the existing video controller and then write a separate block which is kind of an address translator, so that when the VGA system is looking, it looks like it's sending to a single thing, but
Oh, the pain. Okay, I see what you're doing. So you're going to say, I'm going to have a single block. I'm going to have so the VGA controller is going to see a single block of memory as it always has. So you're going to have communication back and forth to the memory. So that's one port. And then there's going to be another port of this memory, which is written to by a muxer that then has several memory blocks on it.
Yeah, and solver writes to those.
And the solver writes to these. This should work. I'm not sure it's less work, but it'll work. There's another way of doing this too, but I'm not going to talk about that right now. So you could do this as long as you have enough memory. Because there is a serial bottleneck here. And so you may need to have as much memory here as you have here.
So what I was thinking is like not having a memory there, just an address translator so that it just goes to the other memory directly. Kind of VGA sends an address, it just figures out which block it is and sends the address from there and gets the data. And sends
There's still a serial bottleneck here, right? There's only one write can happen at a time. So you could have 29 solvers stalled, waiting for that one serial connection, no matter how you do that, where that serial connection is. The advantage of going to this multi-block system is that there is no muxer in there. The muxing is at the output, but since you know the order in which you have to transition, you have to traverse memory for the VGA output, you don't have a conflict on this side between serialization because the VGA is, in fact, serial. So I think this will suffer from the same parallel serial bottleneck, just in a different spot. Floating. That's a chunk. That's interesting. Up until 3 years ago, every project had to have a student implemented VGA controller because the QSys didn't exist before then very much. So this is certainly doable. Floating point. You know how IEEE 754 floating point works? Do you know what the format is? Anything about it? Are you ever taught that someplace or another? In computer architecture or something? So there's the word, the 32-bit word is divided into a 1-bit sign bit, an 8-bit exponent, and a 23-bit mantissa, although the correct term is significant, but we'll call it mantissa. So you have this is not 2's complement. This is sign magnitude, unlike everything else you've seen this semester. The sign is 0 for positive, 1 for negative. There's an 8-bit exponent in 128 offset binary. So 2 to the 0 has the value 128. So the exponent is binary, and the 23-bit mantissa is effectively 24 bits because there's a phantom bit out here which is always 1, and so it's not recorded. That means that you always have to normalize the mantissa, so the highest order bit is 1, and you change the exponent so that the normalization works out for the number you want to store. So you get 24-bit accuracy even though you're only storing 23 bits because there's an implicit 24th bit. Well, And full IEEE floating point not only has this format, it has special values for positive infinity, negative infinity, not a number, illegal number, and a few other items. All in all, it requires a couple of thousand ALMs to implement a floating point add in IEEE format. It's too big to be handy. So what some students have done, and I've worked on too, but mostly with student work, have been to chop down the floating point format into something slightly more handleable. First of all, you throw away all the special cases and say, if there's an underflow or an overflow, it's dead. Don't do that. If there's a positive infinity or a negative infinity, you're making a mistake. Because no real value ever gets that big. So all the special cases are gone, and the format is changed into one sign bit, 8 exponent bits, and so that's 9 and 20, total of 27 bits. 27 bits, and so we have 27 minus 9 sounds like 19 bits of mantissa.
Wait, 18
18
bits with
bits.
an implicit 19 bit.
18 bits with an implicit 19th bit, yeah. So that's the format that the students came up with. And it's pretty fast. Students wrote floating point add. You put in 2 floating point numbers in a clock because it's got a 2-stage pipeline in it for speed. I modified a version to make it combinatorial in case you didn't like the pipeline. It'll work, it'll do an add at 50 megahertz, but maybe at 100 and maybe not. Whereas this will work at below 100 megahertz. Floating point multiply, which takes less work than an add in floating point. Floating point inverse square root. Floating point negate. That's easy. Just flip the sign bit. Absolute value, 0 the sign bit. Compare. Harder than it looks. And then one I've never seen anyplace else, and that's floating point shift. So a floating point shift just increments or decrements the exponent, multiplies and divides by 2 without actually using a multiplier. It just changes the exponent by 1, or by any number you want, actually. And then into floating point to int. So there's enough. Oh, there's also 2 utilities that run on the HPS that take in a float and put out this range set 27 format, or take range 27 format and turn it back into a float. It's pretty fast, pretty well tested. It would work for this lab if you want to play with it. I did use it to test it. I wrote that digital differential analyzer you did in lab 1. I converted it into floating point just to see what would happen. So the floating point is not much worse, it's a little worse, but the results are quite accurate, it works quite well. Particularly when you go away from Euler integration to Hume's method, which makes it significantly more accurate. So there are some examples of how to use the floating point, which would be important if you actually decide to use this in lab 3. So there's a lot to think about for lab 3, because that makes life interesting. There's how are you going to optimize the pipeline? Are you going to make it a serial pipeline with 1 multiplier? Are you gonna use 3 multipliers and make it a parallel pipeline? How many pipelines can you fit on the FPGA? How much memory does it take to display a VGA image? Is there enough? Oh, interesting question. How much memory does it take to display a VGA image? Well, I happen to know off the top of my head it's 302,700 pixels on the display. And we have, in memory, we have about 4 megabits of M10K block. 4 megabits is about half a megabyte, so 500 kilobytes, which is enough to, so if you use 60% of internal memory, you have enough memory to completely describe the VGA image. So you have enough ROM blocks here, or RAM blocks here, to do that. Gosh.
How many bytes is that giving to each pixel?
1 byte.
Okay.
You do not have enough to do 2 bytes. Because a hasty calculation shows that it requires 600 kilobytes. So you only have 500. So you're limited to 8-bit color, but you only need probably 10 different colors. Because remember, you're going to produce a color proportional to the log of the number of iterations. So about 10 or 20 colors is going to be more than you possibly can need for this. I think I'm displaying 8 here, or 9. And so you could go to 4-bit color, as long as you choose the colors correctly. So what that says is, you'll read back a color index from memory, which will be either an 8-bit or a 4-bit index. Then you'll have a lookup table, which will convert each index to a different color. Then that lookup table output will go to the I-red, I-green, and I-blue inputs of the VGA controller. So there is enough memory, but there's not too much more than enough memory. The pipes themselves are going to take very little, the solvers themselves are going to take very little memory. So in this case, you should not be memory bound by the solution. You'd be memory bound by the display. So I spammed you all with Piazza post yesterday. I think they're still cleaning the drains, is what they're doing. With ideas for final projects. Did any of them sound interesting? I particularly like that head-related transfer stuff because that is an essential piece of virtual reality, the hearing aspect. VR is dominated by sight-oriented devices because some people seem to think that humans are sight-oriented, but in fact audio is at least as important for getting around and for understanding the world. So making a head-related transfer system that calculates the way a sound will come from some arbitrary location in space as you turn your head is a non-trivial undertaking. I put a link in there to an IEEE article, IEEE Spectrum article, which came out last week. It's really interesting about how it turns out when you turn your head, the way you get the direction of sound changes because of refraction off of your shoulders. Oh, the pain. So that means that the virtual reality system has to know the shape of your body to calculate the sound direction properly. So the amount of calculation increases without bound depending on the accuracy you want, but you can do pretty well by looking at the straight ahead head-related transfer function, assuming you're actually not turning your head very much. It's different for everybody. Depends on the shape of your ears. Ears are weird. You ever look at ears? Ears are weird. Everybody's ears are slightly different, and each one of them is a custom-made